So now you're on the air. Yeah.
Okay. So welcome to Henri Darmon, who will give a talk in our online seminar of today. He is going to talk about complex multiplication for real quadratic fields and modular forms of weight 3 halves.
Okay. So thank you, Francesca, and thank you for inviting me to give this talk. So I'm going to begin by saying a few words about the backstory for this lecture. So in fact, I was supposed to give this talk live in person in March. On March 1st, in fact, on Sunday morning, I landed in Barcelona. And after settling into my hotel, I took a nice, a pleasant stroll on the Barceloneta and prepared what was going to be the lecture on Monday morning. But then when I got back in my hotel, I had a frantic message from Victor telling me that the seminar was canceled because there were some fears over this COVID-19, which at the time was much less present in our minds than it is now. Nonetheless, for the rest of the week, I had a very pleasant stay in Barcelona. I met up with Victor every day. We had nice meetings with Marc, Chevy, and Xavi on Tuesday, and later with Luis, Nuno, Oscar. So I really had a wonderful time that week in Barcelona, and I want to take the chance now to thank all of you for your wonderful hospitality during that week. And here's actually the sole picture I saved from that visit. Victor and I in some nice restaurant, having lunch in Barcelona in a place which was actually pretty well socially distanced. I mean, you can see that the surrounding tables are pretty much empty. Okay, so I'm going to begin by saying a few words about the collaborators. The talk I'm going to give is a fairly general overview of a number of past projects. I'm going to report first on some joint work with Alice Pozzi and Jan Vonk. And it also involves, though, some earlier results that I obtained with Alan Lauder and Victor. And in time permitting, I also hope to touch at least a little bit on an ongoing project with Yingkun Li and Jan as well. Okay, so I'm going to start by giving you a little bit of the background for the talk. So the goal of the entire project is to extend the theory of complex multiplication in the setting of real quadratic fields. So Victor asked before, why complex multiplication? I don't know, but anyway, the general term complex multiplication, of course, as you all know, refers to the program of generating class fields of imaginary quadratic fields and also interesting arithmetic objects over abelian extensions of imaginary quadratic fields. The prototypical objects are values of modular form that CM points. And the CM points themselves, or their orbits under a group like SL2Z, are naturally indexed by ideal classes of imaginary quadratic fields. And these values are generally of great arithmetic interest. So they give us a handle on explicit class field theory for imaginary quadratic fields. And they also give interesting instances of Euler systems, which are, of course, something of a cottage industry in Barcelona. So elliptic units, which give us a lot of insights into the arithmetic of abelian extensions of imaginary quadratic fields, and also of elliptic curves with complex multiplication, and Heegner points, which give us the best information we have still now on the Birch-Instrument and Dyer conjecture for elliptic curves over the rationals. And so it's quite a rich structure we have at our disposal over abelian extensions of quadratic imaginary fields, and it's natural to ask whether these structures might extend to other settings. And maybe the most basic one is whether these structures could make some sense over real quadratic fields. And so the hope is that this theory of complex multiplication, which has so many interesting applications and ramifications, does extend to the setting of real quadratic fields. And the hope is that it does, and the key idea which underlies our approach is to replace classical modular forms by something else, which are still avatars of classical modular forms, but are somewhat less familiar. And this is what we call rigid analytic or meromorphic cocycles. And so now to motivate that concept, I'm going to go back to the origins and present you with a simple prototypical example of somehow extending the theory of complex multiplication to the setting of p-adic uniformization of Shimura curves, so to speak. So rather than here in this discussion, rather than striving for the maximal generality, I'm going to focus on a very special case, which is sufficient to illustrate to the general notions I want to then generalize. So we're going to let H be a definite quaternion algebra, and for the sake of being definite or specific, I should say, you can think of the skew field of rational Hamilton quaternions over the rationals. And I let R be a maximal order in that ring of quaternions. For example, the standard maximal order, which is here defined by Hurwitz, generated by I, J, and 1 plus I plus J plus K over 2. Now, I let gamma be the multiplicative group of elements of norm 1 in this ring where I've inverted P. Now, this R is if I just took R1 star, I would get a finite group, which is isomorphic essentially to a group of order 24. It's a central extension of A4. But when I invert P, I get a group which is quite a bit richer, which is now a discrete, which is a group which is infinite, but acts discretely on the p-adic upper half plane. And Jacques Langlais tells us that the first cohomology of this group is isomorphic in a non-canonical way to the space of weight 2 cusp forms on gamma naught of 2p, the new part of that, as a Hecke module, as a module over the ring of Hecke operators. And therefore, modularity tells us that if we have an elliptic curve of conductor 2p, then there is a Hecke eigenclass in this first cohomology, which has the system of Hecke eigenvalues. So when I wave my cursor over the lines, do you see something? If I
Yes.
You see, yeah, you see the cursor. Okay, so I can point.
Yes.
So we have this eigenclass phi sub e, which has the property that if you apply the Elf Hecke operator to it, you multiply the class by the corresponding coefficient AL of E, which is the usual Fourier coefficient of the cusp form attached to E, or L plus 1 minus the number of points on the elliptic curve over the field with L elements. So that's what modularity tells us. So we can try to see whether this Hecke eigenclass can tell us something more directly about the arithmetic of the elliptic curve. So this cocycle, it encodes the periods of a rigid analytic function. So I'm going to let HP be the Drinfeld p-adic upper half plane, the complement of P1QP and P1CP. And we can express this HP as an increasing union of these subsets, HP greater than epsilon, which is a set of Z's which are at distance, at least epsilon in the p-adic metric, from the boundary. So the points in ZP squared prime, the primitive vectors in ZP squared, I think of as elements in the boundary, P1QP of the upper half plane. And so if I take points which are distance at least epsilon from the boundary, I get a region which looks like a complement of a larger and larger number of smaller and smaller p-adic disks that I'm deleting. And I can write HP as a union of these. And we say that a function on the HP is rigid analytic if its restriction to all these subsets, which are called aphenoids, can be written as a uniform limit of rational functions having poles outside the region. Okay, so that's the kind of naive, it's fairly down-to-earth, lowbrow definition of a p-adic analytic, a rigid analytic function in this context. So if P is an odd prime, we can fix an identification of the Hamilton quaternions over QP with the 2x2 matrix ring over QP, and thereby embed the group gamma in SL2QP, and therefore this group gamma acts discretely on the p-adic upper half plane by Mobius transformations. So now we can try to trivialize this one cocycle, this phi e. Remember, this was defined purely in the setting of group cohomology as the set of homomorphisms on this discrete group gamma. And so I let A star be the group of nowhere vanishing rigid analytic functions on the p-adic upper half plane. And then a theorem, which follows from the theory of Mumford and Tate and the theory of Cherrin and Grinfeld of p-adic uniformization of Shimura curves, is that if we let Q sub E be a very specific p-adic scalar, namely the Tate period of the elliptic curve over QP, so E is the elliptic curve which corresponds to the system of Hecke eigenvalues that I had to start with, then I can produce a rigid analytic function, which I'll call J sub E, which has this property. It's not quite invariant under the group gamma, but if I translate Z by gamma and take the ratio, I get a certain power of the Tate period, and the power is dictated by this element in H1 of gamma, this phi sub E. So in this way, this Q sub E to the power phi sub E is a one cocycle with values in the multiplicative group of scalars, and it becomes a one co-boundary in the larger group of multiplicative functions on A star, a group of analytic rigid functions. So this function J sub E, of course, now, this is now an element of H0 when I view it with taking values in A star modulo powers of Q, since phi sub E is Z valued, the obstruction to this being a co-boundary is, or I should say a cocycle, is given by this discrete subgroup, Q sub E to the Z. So this function is, in fact, just a modular parameterization from the Shimura curve of level 2p to the elliptic curve. Namely, it induces a natural function on the set of gamma orbits on HP, taking values in the quotient of Cp star by this discrete subgroup QE to the Z, which is just the Cp points on the elliptic curve. And one interesting application of this modular parameterization is that it allows us to generate interesting points on the elliptic curve, the so-called Hegner points. So we have a notion of a CM point on the p-adic upper half plane as being any point tau whose stabilizer in H star is the multiplicative group of a quadratic subfield of H. Because H is a definite quaternion algebra, such a quadratic subfield is automatically an imaginary quadratic field. And moreover, the primes 2 and p are non-split in this quadratic imaginary field. And the theorem then is that if delta is any degree 0 divisor on the p-adic upper half plane, which is supported on CM points attached to K, then the image of delta under this modular parameterization is a point on the elliptic curve over Cp, of course, but this point is actually algebraic and it's defined over a ring class field of K. And so that gives us quite a strong handle, as you know, of all the theory of Kolyvagin, and all these wonderful results, Gross and Zagier, and so that we have on the arithmetic of elliptic curves are ultimately based on this very rich structure, allowing us to construct points systematically over abelian extensions of imaginary quadratic fields. So I want to sort of now describe how this might extend to the setting of real quadratic fields. And the basic idea is to replace the group gamma that we had before by a discrete subgroup of an indefinite quaternion algebra. And the basic example of that, the simplest special case, is SL2Z of 1 over P. Okay, so I'm going to let this group gamma now be this group acting on HP by Mobius transformations. And the main difference now is that because this quaternion algebra is not compact at infinity, it's not definite, it doesn't give rise to a group which is compact at infinity, it's quite a bit larger than it was before, and in particular does not act discretely on the p-adic upper half plane. And the first cohomology of gamma is rather poor. It's if we take it in z coefficients, it's completely torsion, and with rational coefficients, it's trivial. So there are no interesting Hecke eigenclasses to be found in the first cohomology of gamma. And what one sees then is that the interesting cohomology of this group, this so-called Ihara group, occurs in degree 2. And in fact, one can express the group gamma as an amalgamated product of two copies of SL2Z which intersect in a common subgroup which is isomorphic to gamma naught of P. This can be seen by making gamma act on the Brouat-Titz tree of SL2QP, which is a p+1 regular tree with vertex stabilizers SL2Z and edge stabilizer isomorphic to conjugate copies of gamma naught of p. And from this expression of gamma, one can calculate the cohomology of gamma and relate it to the cohomology of gamma naught of p. And one finds in particular that the second cohomology of gamma is essentially identified with the first cohomology of gamma naught of p in a way which is completely natural and compatible in particular with the action of Hecke operators. Okay, so modularity therefore tells us that if we have an elliptic curve of prime conductor p, then there's a Hecke eigenclass in the second cohomology of gamma, which satisfies this familiar relation, right? That the Hecke eigenvalues are the same as they are for the modular form attached to the elliptic curve. And so now we can try to ask ourselves whether we could exploit that cohomology class to produce invariants that are rich enough to tell us something new and interesting about the arithmetic of E. So we can try to trivialize this 2 cocycle phi sub E. Now, around 2000, I made an observation, which is to a large extent is what got me started on this whole program of real multiplication. And the theorem is this. It says that there's a 1 cochain on the Sihara group with values in the multiplicative group A star, and which satisfies this kind of 3-term condition. So if you take the image of this 1 cochain under the 1 coboundary, which defines the usual complex which calculates group cohomology, then you get the 2 cocycle Q sub E to the phi E gamma 1 gamma 2, where Q sub E is again the Tate period of the elliptic curve. So this is a striking instance of how the Tate period comes up out of considerations arising only in group cohomology. So if I took any other p-adic number here, anything which gives rise to a lattice which is not commensurable to Q sub E, I would not get this kind of trivialization result. So it's crucial that we work with this. And this theorem turns out to be a rather formal consequence of the exceptional zero conjecture, which was formulated by Maser Tate Teitelbaum in the early 90s or late 80s, I guess, around 1987, and then proved by Greenberg-Stevens in 1990. So I like to say that this result was proved 10 years before it was stated. All the key ingredients were in place then. The main point was to recast the statement, which was initially a statement about derivatives of p-adic L functions, into a language which involves only, to a framework which involves only the cohomology of the Ihara group. Okay, and that statement then suggests that the cocycle, the 2 cocycle phi sub E, and so thanks to this theorem, we get a 1 cocycle with values in A star mod Q to the Z, which I'll talk about on the next slide. And I want to emphasize that this result, the non-formal aspects of the proof, arise in the work of Greenberg-Stevens, and they're strongly based on the notion of p-adic deformations of modular forms and their associated Galois representations. Okay, that's a crucial ingredient. And therefore, I want to emphasize also that this proof differs very much from the proof of Cherenek-Drinfeld that I alluded to earlier in my slides, which relies on very geometric ideas. The statement that the quotient of the p-adic upper half plane by a discrete group is the CP points of a Shimura curve, and so on and so forth. All of these geometric ingredients are not available to us, and we had to kind of follow this less direct route based on deformations of Galois representations. Okay, so thanks to this relation, you see, this tells us that J sub E satisfies a cocycle relation, but modulo powers of Q sub E, this Tate period. And so we get, in particular, the class of JE in the first cohomology of gamma with values in this group. And we call this the rigid analytic cocycle attached to our elliptic curve of conductor P. And well, now what can we do with this 1 cocycle? If we have a tau in the p-adic upper half plane, there's a so-called evaluation map from A star to CP star, which simply sends a function to its value at tau. Okay, now it's tempting to try to use this evaluation map to define a homomorphism from the first cohomology of gamma with values in A star mod Q to the Z to the first cohomology with values in this quotient, right? We're just evaluating at tau, so we map A star to CP star. However, we have to be careful because the evaluation is not gamma equivariance, right? The group gamma is permuting the elements of the p-adic upper half plane. And so this evaluation is not compatible if we endow Cp star with the trivial action of gamma. However, it is equivariant under a subgroup, namely the stabilizer of tau in gamma, which I denote gamma tau. So we have a natural map like this. And of course, if the stabilizer of tau is trivial, then the target of the evaluation map is trivial, and this map is not very interesting. But what makes it interesting is that there is a set of taus for which the stabilizer is non-trivial. Namely, the stabilizer is non-trivial precisely when tau generates a real quadratic extension of Q, generates a real quadratic field. And in those cases, gamma tau is isomorphic to Z. And the identification can be even made essentially canonical up to torsion by choosing certain orientations on the p-adic upper half plane. Okay, so that allows us then to define the value of the cocycle at a real quadratic point. And we define it in this way. So we define the value of JE at tau to be the value of the cocycle JE at the stabilizer. So gamma tau is a generator of the stabilizer of tau and gamma. This gives us an analytic function on the p-adic upper half plane, and then we evaluate this function on tau. And that sort of captures this evaluation map. That's what we call the value of J sub E at the Rm point tau. Okay, so now once we have this object, we can evaluate it, of course, and if tau is an Rm point, or which generates a real quadratic field F, then the conjecture we make is that the value of this cocycle JE at tau is a global point on the elliptic curve, which is defined over a suitable ring class field of the real quadratic field F. So in that sense, this object J sub E really appears to have a lot of arithmetic content. It really plays the role of a modular parametrization in the setting of this theory, and it should allow us, at least conjecturally, to construct a rich supply of algebraic points on the elliptic curve. Now, these Rm values are what we call Stark-Heegner points, and because in some sense they're to Heegner points, what Stark units are to elliptic units. That's really the idea behind this notion. Now, this conjecture on Stark-Heegner points touches on a basic mystery, which is how do we construct algebraic points on elliptic curves using based on structures which are independent of the theory of complex multiplication. So for now, I think it can be said that the theory of complex multiplication and its generalizations due to Shimura, Taniyama, and many others are really the only non-conjectural avenue we have to producing points on elliptic curves. So it would be very interesting to have more insights into this question. Now, the definition and calculation of these Stark-Heegner points has been significantly extended and generalized. However, there's been a lot of work by Matt Greenberg, Matt Krzyzkowicz, Ksevi Guitart, and Marc Masdeu did a lot of lovely work extending the method to other settings and developing very good algorithms for computing these points in practice. So there's, of course, a lot of experimental evidence that this conjecture is true, as you all know. Okay, so if you want to get a better insight into this problem of how do you construct algebraic points on elliptic curves via this theory, we'd like to flesh out the theory further. And one way we can try to do this is by backtracking a little bit and trying to see whether this theory has more concrete and less mysterious manifestations. And the first setting is to try to replace the cusp form attached to an elliptic curve by an Eisenstein series. And this leads to what's called the Dedekind-Rademacher cocycle, which arose more or less in Samit Dasgupta's PhD thesis around 2004. And the starting point is that the group H2 of gamma Z, where gamma still is our Ihara group, is essentially identified with the first cohomology of gamma of P, and that first cohomology contains an interesting class, the so-called, which is Eisenstein for the Hecke operators. So Eisenstein, in the sense that Hecke operators act with the usual eigenvalues, as on this, the same as on an Eisenstein series of weight 2 and level P. And this Dedekind-Rademacher homomorphism just encodes the periods of a modular unit, delta of Pz over delta of Z. So this is a modular function of, so modular form of weight 0 if you want, on gamma naught of p, and its logarithmic derivative gives us this Eisenstein series of weight 2 on gamma naught of p. And its periods, the extent to which its logarithm fails to be invariant under gamma, is given by this Dedekind Rademacher homomorphism, which I call phi sub Dedekind Rademacher. And what Samit and I proved in 2003, and in a slightly weaker form, which was later strengthened a little bit in this work with Alice and Jan, is that there's a one cochain on gamma with values in A star, which for all gamma 1, gamma 2 satisfies this relation. So the exactly same relation we had before for the elliptic curve, except that now the Tate period, Q sub E, is replaced by a much simpler period, which is simply the prime number P, which of course generates a discrete subgroup of CP star. And so we get this kind of trivialization result. And the image of this J sub Dedekind Rademacher in the first cohomology of gamma is what we call the Dedekind Rademacher cocycle. Okay, so then it was very natural to make the conjecture that the values of the Dedekind Rademacher cocycle at Rm points are global units in the corresponding ring class fields. And in fact, global P units, so elements that whose prime factorization involves only primes above P. And this, then the main point I want to make now is that this conjecture is much more tractable than the conjecture on Stark-Heegner points, for which we have relatively less theoretical evidence. And there is, in fact, now substantial theoretical evidence for this conjecture. And I want to talk to you now a little bit about why that is and what are the basic structures that allow us to prove a non-trivial results in this direction. So the point is that the conjectural P units, the values of the Dedekind Rademacher cocycle at Rm points, can be related to gross Stark units. So if F is the field generated by Q of tau, and psi is some character of the narrow class group of F, or maybe more generally, any function on the narrow class group, like the indicator function of the ideal class generated by 1 and tau in the group of fractional ideals of F, then we can form an L function attached to this function by simply summing the norms of ideals to the minus S multiplied by the value of this function on the ideal class, so taking the sum over all ideals of the ring of integers of F. And this L function admits a p-adic avatar, which was defined by Deligny and Ribet. It's attached by them to any totally odd character of a totally real field, in fact. And so we can look at this p-adic L function. And we can also, on the other hand, consider a slightly coarser invariant associated to the values of the Dedekind Rademacher cocycle, which I call J sub Dedekind Rademacher plus. And that's simply taking the product of the value at tau times the value at tau prime, where tau prime denotes the conjugate quantity. So tau is defined over the real quadratic field F. This F has an involution, which sends root d to minus root d. And if I take this conjugate thing, I'm then just taking the norm from qp tau down to qp of the Dedekind Rademacher, of the value J Dedekind Rademacher at tau. Okay, so this is what I call the J Dedekind Rademacher plus of tau. And it turns out that there's a connection between this value, this invariant, and the p-adic L function. And that was something Samit and I proved already in this first work in 2003, that the logarithm of this value is equal to the first derivative at 0 of the Deligny-Ribet p-adic L function twisted by this function psi. And therefore, we were able to see that its algebraicity would follow from an older conjecture, the p-adic gross Stark conjecture. And that somehow gives further justification for the terminology, Stark-Heegner points. And so it shows that these invariants are intimately connected to the kind of objects that you see appearing in the Stark conjectures because of their intimate connection to L functions. Okay, so I want to say a few words quickly about the proof of this theorem, which I've reproduced now on this slide, okay? So the original proof that was in Samit's thesis relied on a direct comparison between the value and the derivative of the p-adic L function And it rested on the construction of the cell function due to Kasuno guess. And that approach has been extended quite a bit, notably in later work by Pierre Charolois and Samit Dasgupta. It's been extended to arbitrary totally real fields and led to quite a lot of nice work, which in fact you might be hearing about next week, since I know that Samit is giving the next lecture in the Barcelona Seminar. So I'm not going to say too much on that. But what I want to do say something about is an alternate approach, which is inspired by a proof of Siegel for the rationality of the L functions. And that alternate approach works only for real quadratic fields, but has, so in some sense is much more special than the general approach that Samit has been developing. On the other hand, it does represent some advantages, which I'll get to at the end of my talk. Okay, so to say something about that alternate approach, I need to introduce a special kind of rigid analytic cocycle, which is different from the Dedekind and Rademacher one. It's what Jan, Alice, and I call the winding cocycle. So this is based on taking, okay, so I remind you here, this is the usual notation for the cross ratio of 4 complex numbers, or 4 p-adic numbers for that matter. And if Z1 and Z2 are 2 elements of the extended upper half plane, now complex upper half plane, I'm going to use this notation, Z1, Z2, to denote the hyperbolic segment joining Z1 and Z2. Okay, so, and then I also am going to use this notation for the intersection product of 2 hyperbolic segments on the hyperbolic upper half plane. So the intersection number is exactly what you think it is. There's a sign convention that you have to be a bit careful about that involves choosing an orientation on the upper half plane, which is crucial in computation, so I'm going to suppress that for the lecture. You can imagine what the convention would be. Now, if I fix a base point C in the complex upper half plane, and another base point eta in the p-adic upper half plane, so this definition is going to involve 2 choices of base points, then I can consider the following infinite products. So it's going to be a function which depends on an element gamma in the Hara group and a p-adic number z in the p-adic upper half plane. And what I do is I take the product of the function z eta alpha 0 alpha infinity. So this is the function which has a 0 at alpha of 0, a pole at alpha infinity, and I'm taking this function and I'm evaluating it at z and dividing by the value at eta. And I'm raising this cross ratio to the power the intersection number between the hyperbolic segment joining alpha and 0 alpha infinity and the hyperbolic segment joining c and its translate under gamma. Okay, so this is a bit of a lot to take in, but it's somehow a product, an infinite product, which this exponent here has the effect of cutting down the number of factors, because very often for many values of alpha, this hyperbolic segment will not intersect at all the other hyperbolic segments. You'll get a 0 here. And it turns out that this infinite product converges to a non-trivial rigid analytic function on the p-adic upper half plane. And moreover, it satisfies a cocycle property like this, modulo scalars. So it's not quite a one cocycle, but modulo multiplicative scalars it is. Okay, so it's kind of believable given that this looks vaguely cooked up to have some kind of gamma invariance property because we're taking a product over gammas in the group, etc. Oh, I'm sorry, there's a typo here. This product should be, this gamma here should be an alpha. Okay, so I'm taking the product over all the alphas in gamma. Okay, sorry about that. And the gamma here is fixed, yeah. Okay, so this is the definition of the rigid meromorphic, rigid analytic cocycle, which we call the winding cocycle. And unlike the Dedekind and Rademacher one, this one has a very explicit infinite product defining it, but this winding cocycle is not an eigenclass for the Hecke operators, which is both an advantage and a disadvantage. I mean, the advantage is it has a much more explicit definition. And what we proved with Alice and Jan is that this winding cocycle can be expanded as a linear combination of the Dedekind and Rademacher cocycle and the cocycles J sub f associate to various Hecke eigenforms on gamma naught of p. So we can write it like this, and the scalars that appear in the expansion are essentially the algebraic parts of the L functions of the various modular forms at the central critical points, divided by an appropriate period to make it algebraic. Okay, so then we get this kind of spectral expansion. And as a corollary, if we form this generating series where we just take the sum of the logarithms of the values of the winding cocycle at the Hecke translates of a given tau times q to the n, so I have a tn here and a q to the n there. I can look at this formal generating series. Then I get a modular form, I get a modular form of weight 2 on gamma naught of p with a very precise value of the constant. The constant has to be the value of the Dedekind Rademacher cocycle at tau, or rather its p-adic logarithm times a simple rational factor. So therefore, we've interpreted the value of the Dedekind Rademacher cocycle as in terms of a modular generating series. Okay, on the other hand, we can give an independent formula for the same generating series in terms of the diagonal restrictions of Hilbert modular Eisenstein series. So I can consider the Eisenstein series of weight k attached to this function psi on the narrow class group, and here's this, it's given by an explicit expression, and this function, this Eisenstein series, is invariant under the full Hilbert modular group, SL2OF. And if you stare at the coefficients, you realize that these coefficients essentially behave as p-adic analytic functions of the variable k, of the weight variable, at least if you perform a small operation on it, of so-called p-stabilization, which has the effect of making it invariant under a slightly smaller group, the sort of Hecke congruence group of level p on the Hilbert modular group. So you have this kind of p-stabilized Eisenstein series where you kind of replace the divisor function by a modified divisor function where you sum only over divisors that are prime to p. So somehow the usual yoga for constructing p-adic families of Eisenstein series. And the constant term in this Eisenstein series is the p-adic L function that appears in the Gross-Stark conjectures. And likewise, okay, here this is the explicit formula for the coefficients of the Eisenstein series. So what we then see is that the Fourier coefficients of that Eisenstein series, the p-stabilized one, extend to p-adic analytic functions of the variable k. So now what we can do is we can take this Eisenstein series and restrict it to the diagonal. So a Hilbert modular form is naturally a function on 2 copies of the upper half plane, and you look at the single upper half plane embedded diagonally. In other words, I'm going to get this gk of psi, which is now an elliptic modular form of weight 2k on the Hecke congruence group gamma naught of p. Okay, so that's my gk psi. And the first result is that when p is inert in the real quadratic field, the weight 1 specialization of this family vanishes identically. And that's a very interesting situation, because when you have a family of modular forms and it vanishes identically at a point, the general philosophy, which goes back at least to this wonderful program of Kudla, is that one should consider then derivatives of these families with respect to the varying parameter. And so we can consider the derivative of this diagonal restriction of the Hilbert modular Eisenstein series with respect to the weight variable k at k equals 1. So that's the derivative in weight 2 of this diagonal restriction. And we get some explicit generating series. And it's a p-adic, we know what its 0th term is. That's still the same. It's still the derivative of the Liebner L function attached to the character psi at s equals 0. And then we get some other coefficients. And this p-adic modular form has the feature that if you take the limit of a sub np to the t, where a sub n are these coefficients, a of n here, then you recover the logarithm of the winding cocycle, JW plus, evaluated at Tn tau, where tau is the Rm point, which is associated to this indicator function psi. Remember, psi was the indicator function of the narrow ideal class attached to tau. So this is what you get out of this generating series. So you have an independent way of considering the same generating series, which makes the winding cocycle appear. So we can now rephrase this as a statement about what is the image of this overconvergent modular form under the ordinary projection operator, right? So, oh, sorry, I should move down. So this modular form is imaged under the ordinary projection of the derivative of the diagonal restriction of the Hilbert modular family of Eisenstein series, has a Fourier expansion which is given like this. So the constant term is the derivative of the p-adic L function, and the other coefficients are given by these values of these Dedekind and Rademacher cocycles. And this is a modular form of weight 2 in level P. Now it's a classical modular form because the derivative was only a p-adic modular form living in some infinite dimensional p-adic Banach space of overconvergent modular forms. But when we took the ordinary projection, we mapped it down to a classical modular form living in a finite dimensional space. And on the other hand, we had already shown independently that this generating series, involving the logs of the values of the winding cocycle, is also a modular form of weight 2 in gamma of p. But now the constant term involves the value of the Dedekind Rademacher cocycle, or this slightly weaker invariant J Dedekind Rademacher plus, evaluated at tau. So if you look at these two results, we see that these two modular forms differ. Well, I mean, all their coefficients agree, therefore their constant terms have to agree. And it follows, therefore, that the derivative of this p-adic L function is equal to a simple multiple of the value of the Dedekind Rademacher cocycle at tau. And that's how we can prove this result that that already appeared in Samit's thesis. And this new approach is somewhat reminiscent of the analytic proof of the theorem of Gross and Zagier on factorizations of singular moduli, which also involves a diagonal restriction of a family of Eisenstein series, and in fact, of Hilbert Eisenstein series. And this is in fact how that approach was suggested to us. Now, once we know this, well, what progress have we made? Well, we know that the values of the Dedekind Rademacher cocycle tau follows from the p-adic analog of the star conjecture that was proposed by Gross. And so that means that all we have to do now to understand these values is to prove the p-adic star conjecture. Now, that might seem a little bit daunting, but fortunately, the p-adic star conjecture is much more tractable than its Archimedean counterpart, on which there's been very little progress since the days when Stark formulated it. The p-adic one is much more manageable, and in 2007, with Rob Pollack, Samit and I, showed that the p-adic gross star conjecture is true in a sufficient generality to encompass this case that we were interested in. In particular, the value J Dedekind Rademacher plus of tau is up to torsion a p unit in the narrow Hilbert class field of F. Yeah, that's the theorem that we proved in 2007. And that proof was based on somehow carefully analyzing the p-adic cuspidal deformations of the Eisenstein series of parallel weight 1 in the parallel weight direction and of their associated p-adic representations. There was already somehow the idea of exploiting deformations of Hilbert modular forms was already present was also present in that work on the p-adic star conjectures. Okay. So the problem, though, that arises now is that this algebraicity of J Dedekind Rademacher plus, it implies that J Dedekind Rademacher of tau is an algebraic number, but only up to multiplication by elements of norm 1 in the multiplicative group of the quadratic extension of QP. So that's quite a rather weaker statement than what we'd like to show. We'd like to get the algebraicity of the full invariant. So we'd like to do away with this ambiguity, which is somehow built into the framework of the gross star conjecture, which only considers derivatives of p-adic L functions relative to a certain variable, which you might view as a cyclotomic variable, so to speak. And recent work by Samit Dasgupta and Mahesh Kagde has achieved a remarkable progress in this direction, which you'll probably hear more about next week when Samit speaks in this seminar. I'm just going to say now one slide about that work. It's really quite a lovely work. So the first theorem that Samit and Mahesh prove is that the algebraicity of the full invariant, at least up to some small torsion ambiguity, follows from Gross's tame refinement of the Gross-Stark conjecture. So the Gross-Stark conjecture is a p-adic conjecture. One can formulate a variant which involves instead a variable which corresponds to a finite, to the group ring of a finite abelian extension of the totally real field, which is not a ZP extension, but simply has a finite, but ramified at some primes L not equal to P. And that the idea of using such tame refinements is reminiscent of this tame patching technique that arose already in the work of Taylor-Wiles. So that meant that they were able to reduce the full algebraicity to something which is in the same circle of ideas as the Gross-Stark conjecture, this kind of tame refinement. And then they went off and proved the tame refinement. So they also showed in a separate work that the tame refinement of Gross's tame refinement is in fact true unconditionally. And that proof is based on careful analysis of tame deformations of the weight 1-1 Eisenstein series and their associated torsion Galois representations. So that's really a very wonderful development, which gives quite strong evidence towards the algebraicity of the Dedekind-Rademacher values of the cocycle at Rn points. Now, the study of these diagonal restrictions that I mentioned before, that I did with Jan Vonk, can also be refined by considering what you might view as anti-parallel deformations of the Eisenstein series, so deformations in another direction than the parallel weight one. And that leads us to an alternate proof of this theorem of Samit and Mahesh, which is purely p-adic and does not require using tame deformations. And that's the content of this work that I alluded to before with Alice and Jan. And I'm not, well, okay, I'll say a few words about it now in the next few slides rather quickly. So the main result that we prove with Alice and Jan is that there's an infinitesimal deformation of the Eisenstein series of weight 1 attached to 1 and psi in the anti-parallel weight direction, which satisfies the property that when you take the 0th Fourier coefficient of deformation, you get the logarithm of the Gross-Stark unit, of the full unit that you would like to capture, or that you hope to capture with these constructions. And when you take the ordinary projection of the diagonal restriction of this derivative of modular form, which is only an overconvergent modular form, you get a generating series whose coefficients involve, so if you take now you get a classical modular form of weight 2 on gamma naught of P, and when you examine its Fourier coefficient, not its Fourier coefficient, the coefficient is spectral expansion. You expand this out as a linear combination of eigenforms of weight 2 and level P, you get as coefficient the logarithms of the various Rm values of the various cocycles. So you get this kind of expansion. And therefore, we can compare the constant terms again of these of this Eisenstein series and its ordinary projection with diagonal restriction, and conclude that the value of J Dedekind-Rademacher of tau, which is what you see here coming up in this expansion, is equal to the logarithm, or the log of this expression is equal to the logarithm of the unit u tau, and therefore we get this identity at least up to torsion. Okay, so that gives you the algebraicity. Now, I want to emphasize that both the approach of Dasgupta that was kind of developed in this work with Dasgupta and Pollack, and later refined in the tame direction by Samit and Mahesh, and this approach of that I've developed with the Jan and Alice, while they do differ in several key respects, they do have some points in common, and one of them is that they both rest crucially on p-adic deformations of modular forms and Galois representations, which is kind of the workhorse in this for all these results. It's the key tool we have. So deformations of modular forms, Galois cohomology, and global class field theory. These are the crucial ingredients. And you can think of the approach in some philosophical sense as being one where we try to parlay global class field theory, which is valid for any ground field. So global class field theory for abelian extensions of F into explicit class field theory for the real quadratic field F. And there is a parallel in some philosophical sense with the earlier work of Greenberg-Stevens, which also relied very much on the theory of deformations of Galois representations. So I really want to kind of emphasize the importance of that pioneering work of Greenberg and Stevens. And that's not entirely satisfying. It would be very nice to have a more geometric approach. And why would we want to do that? Well, we'd like to defend the claim that this approach to complex multiplication for real quadratic fields based on rigid analytic or meromorphic cocycles has a geometric content that we don't quite understand yet, but that still exists. And one way of defending this assertion would be, well, you observe that elliptic units and Heegner points are related to special values of L functions via Kronecker limit formula or Gross and Zagier formula. So likewise, these objects that I talked about before, the values of the dedicated Rademacher cocycle, the Stark Heegner points, are all related in some way to L functions of certain motives, or certain Artin representations, or certain elliptic curves twisted by Artin representations. On the other hand, there are objects of complex multiplication theory that do not fit into this Stark-like framework. And those are the singular moduli, which are values of meromorphic modular functions, like the J function is the most standard example, at CM points. So these are algebraic numbers which have very interesting non-trivial factorizations and have no immediate connection to L functions. And so our vague belief that the theory of rigid analytic and meromorphic cocycles should have a geometric underpinning would be strengthened if we could find a convincing counterpart of singular moduli that would fit into this framework. And that's what led Jan and I to studying rigid meromorphic cocycles. So rigid meromorphic cocycle is simply a class in the first cohomology of the Ihara group, but now with values in M star, where M star is the multiplicative group of rigid meromorphic functions on the p-adic upper half plane. And whereas the analytic functions mod scalars is a finitely generated Z module, which is intimately connected with weight 2 classiforms on gamma naught of P, the group of meromorphic cocycles is infinitely generated. So it's much larger and richer. And the hope is that we could recover interesting class invariance by looking at the Rm values of rigid meromorphic cocycles, and that they might have interesting factorizations like the values of the J function. And so firstly, we can actually give a complete classification of rigid meromorphic cocycles. So if we let gamma infinity be the stabilizer of one of these, if gamma infinity just be a stabilizer infinity and as a standard matrix of order 2, then it turns out that a rigid meromorphic cocycle, which is trivial on the parabolic subgroup gamma infinity, is completely determined by its values on this one matrix S. And it can be given as a finite product like this, where the alpha taus are rigid meromorphic functions whose zeros and poles are concentrated on the gamma orbit of given tau. So tau is an Rm point. And moreover, the zeros and poles are at taus which are of negative norm and which are positive, respectively negative for the real embedding, for chosen real embedding. So this product involves both Archimedean and p-adic information somehow. And the important thing about this J is that its divisor, the J of S, the divisor of J of S is concentrated on Rm points. And we call this finite sum the divisor of the rigid meromorphic cocycle. And so it's already rather striking that rigid meromorphic cocycles are intimately connected to Rm points via the statement that their divisors are not arbitrary, they're concentrated on such Rm points. And moreover, if you ask yourself, what are the divisors that could arise as divisors of rigid meromorphic cocycles, there's a pleasing connection with modular forms of half-integral weight. And that's where the half-integral weight modular form of my titles comes up. So if we let delta be a fundamental discriminant, which is a square mod P, then we can consider the following thing. We can look at modular forms of weight 1/2 and level 4p, which are weakly holomorphic. That's what these two exclamation points above the m1/2 denote. So what this means, weakly holomorphic, is that these are modular forms which are holomorphic on the upper half plane, but have possible poles at the cusps. And in fact, here I restrict only to modular forms that have poles at a single cusp, which is the cusp, the standard cusp infinity. And I look at weakly holomorphic modular forms with integer coefficients and poles only at there. And then the statement is that given any such phi, there's a rigid meromorphic cocycle, which I call J minus delta phi. So it depends on the discriminant delta, this auxiliary invariant that we chose, and on the modular form phi. And this meromorphic cocycle has the feature that its divisor, its RM divisor, can be read off from the principal part of the input modular form phi. So you don't have to worry about this explicit formula, which is kind of complicated and so, but the main point is that you can read off the divisor of the rigid meromorphic cocycle from the principal part of an input modular form, which is weakly holomorphic of weight 1/2. And that has very much the flavor of the Borcherds lift, which takes as input a modular form of weight 1/2 and produces a meromorphic modular form having divisors at CM points. So this is like very much the same phenomenon. And this rigid meromorphic cocycle, we simply call it the real quadratic Borcherds lift attached to the weight 1/2 form phi. So now our program is essentially to try to establish, so the conjecture that we made in 2019 is that if J is a real quadratic Borcherds lift and tau is an RM point, then the value of J at tau belongs to the narrow ring class field associated to tau and admits an explicit factorization, which depends only on the divisor of the Borcherds lift and on the actual tau that we're putting in. And the strategy that we've been trying to develop to prove this conjecture, so I'll finish my talk by saying just a few very quick words about that, is something we've been developing with Yingkun and Jan over in the last few months. Roughly speaking, we want to show that the values of the Borcherds lift at tau arise inside the Fourier coefficients of certain generating series, which are very much in the spirit of these. So you take p-adic families of certain modular forms of weight 3/2 and look at their derivatives and apply a suitable ordinary projection. And when we examine those coefficients, we see appearing the values of certain rigid meromorphic cocycles. And in that, we're very much inspired by analogous work that's been developed over the complex numbers by many people over the years: Gross and Zagier, Yang, Jan Vonk, Bill Duke, Yingkun Li, Alan, Viazovska. They've all come up with very beautiful results linking up in the complex setting certain, I could say invariants related to values of singular moduli and Fourier coefficients of Mach modular forms. And in the p-adic setting, we can relate these generating series rather directly to certain weight 1 overconvergent modular forms, which I had studied in earlier work with Victor and Alan Lauder. And the coefficients of those weight 1 generating series involve logarithms of algebraic numbers in class fields of real quadratic fields. And so when we kind of put those things together, we see appearing the kind of identities that we would like to establish, so that somehow that, at least there's a lot of computational complications that we're still trying to sort out, but somehow the general philosophy seems to be fairly stable, solid here. And I want to emphasize that these deformations of weight 1 modular forms have been also developed quite a bit later in work with Lauder, Alan Lauder and Victor later, that was very important for us in this project, and also some very nice work later by Victor and Oscar, where they were able to establish quite a bit about the algebraicity properties of these deformations and use them to get really striking results about triple product p-adic L functions attached to the adjoint representations of a weight 1 form. So that's somehow another story, but which ties in very much with this theme. Okay, so I'm going to now end my talk by quickly summarizing what I've said in the lecture. So really what we've been trying to do, I've been trying to do over the last 20 years, and certainly has been for me a very strong guiding motivation, is to try to establish a dictionary between CM theory and what you might call this real multiplication theory, where we replaced a classical upper half plane by a p-adic symmetric space, the p-adic upper half plane of Drinfeld, and replaced a classical group SL2Z by its p-arithmetic avatar, like the Yahara group SL2Z of 1 over p. And then the claim I've been trying to defend and support is that one should replace modular functions by rigid analytic or meromorphic cocycles. And when we, and of course, CM points, the natural counterpart in this theory is simply the RM points on the p-adic upper half plane. And that this leads us, when we evaluate RM at RM points, the rigid analytic cocycles, modulo powers of a Tate period, we get Stark Heegner points, which are the counterpart of the classical Heegner points. The counterpart of elliptic units are the so-called gross Stark units, about which we know a lot now, thanks to the theory of deformations about representation. Singular moduli are now replaced by these RM values of rigid meromorphic cocycles. So that's kind of the general program. And the color coding here, what I've left in red, is meant to denote the objects of which we still do not understand, or we understand very little from a theoretical point of view, the Stark-Heegner points. And in conclusion, I want to say that the approaches that I've described to the problem of establishing this theory of real multiplication is very much based on p-adic deformations, as I've said before, and it leads to a good understanding of some of these aspects, like the Dedekind and Rademacher aspect and the RM values of rigid meromorphic cocycles, but it is not entirely satisfying because it leaves still some mystery, namely the algebraicity of Stark-Heegner points still remains quite a bit beyond what we really understand unconditionally. And so the question that this talk leads to is whether we could have, whether there is a geometric interpretation of rigid meromorphic cocycles analogous to the theory of p-adic uniformization of Shimura curves and the theory of complex multiplication on Shimura curves, which would make the algebraicity of these RM values immediately apparent. That's what we would really like to understand. And the fact that real quadratic singular moduli exist and that they have factorization patterns very similar to what appears in Gross and Zagier, at least in my mind, it very much reinforces the hope that there should be such an interpretation. Okay, so I'm sorry, I think I ran a little bit over time, so I want to thank you for your attention, and thank you very much for your hospitality.
Thank you. So maybe there's one question.
Thank you very much, Henri. This is fascinating.
Oh, you're not at your dentist yet?
I am there. I am there.
Oh, okay.
I am on the waiting room.
Oh, okay, okay. So you're not having your teeth drilled yet, at least.
Well, this is fantastic, Henri. So, do you think this can give new insights for proving the algebraicity of Stark-Heegner points using this approach?
Well, so it's certainly some hope I have. I mean, of course, in our work together, we did have some, and the work we've done with Venirucci, Massimo, and so on, we did have some indirect evidence, right? We were at least able to construct Selmer classes that correspond to Stark-Heegner points. So it would be wonderful if we could bridge the gap between constructing Selmer classes. Selmer classes, again, are just invariance and Galois cohomology, right? So they're not as strong as having global points. But yeah, it would be, it's certainly, that's sort of the dream. I don't have any at all concrete strategy, but I certainly do hope to flesh out more and more the analogy and the connections in the hope that eventually we'll maybe see something that we could try to do. I mean, it would be very nice because it's certainly a barrier in this theory that we have not yet been able to unconditionally construct global points on elliptic curves by any means that does not involve the theory of complex multiplication. And so, for example, the Birch-Instrument and Dyer conjecture, there's been a lot of wonderful progress recently by Skinner and his school, for example, for getting the strong versions of the BSD conjecture at analytic rank 0 and 1 We're very much restricted, particularly in the case of analytic rank 1, to scenarios where we have a CM point construction that allows us to tackle it. So yeah, that would definitely be a very nice thing. So for example, Victor and I, we proved this conjecture, a kind of BSD conjecture for these characters of real quadratic fields, which are totally odd, but in analytic rank 0. And in analytic rank 1, we have a result, but which is quite a bit weaker and doesn't make contact with the complex L function so much. And so that would be kind of the, yeah, certainly one of the goals, if we could do something.
Can I ask an Archimedean question?
Yes.
So one, I mean, you have all these constructions going back to 20 years ago, and you have all these p-adic constructions, and one construction that you mentioned is these ATR points from back in the 2000s, I guess. And do you expect that there is some analog to that for these meromorphic cocycles? So I remember you thinking a long time ago about this, and I don't know if you tried to use now these new insights that you have for these the constructions now to move it to the Archimedean.
Yes, that's a very interesting question. I think it's very interesting. I don't see any. I mean, questions of convergence over the complex numbers are always more subtle, right, and challenging. So it's quite striking that in the p-adic setting, we can define these modular forms or modular cocycles by just taking these naive infinite products. And for convergence, all we need to check is that the general term tends to 1. That's usually quite simple to do. Over the complex, it's more tricky. And I haven't been able so one can ask some very concrete questions. For example, you could ask what the cohomology of the Hilbert modular group with values in the multiplicative group of meromorphic functions on the upper half plane looks like. It's a very concrete question. I don't know what the answer is, and of course it would be very interesting because, as you say, a lot of the statements about Stark-Hagener points have purely Archimedean analogs, which are very mysterious, and in fact, I think I'm convinced that they lie deeper than all the p-adic ones. I mean, we have so much less theoretical evidence for the complex analog, in the same way that the complex star conjecture has seen much less progress than the p-adic star conjecture.
Just because you don't have this Galois deformation techniques.
Exactly. So you might have complex analytic families of modular forms you can tie to the story, but these complex analytic families have no visible connection to Galois representations, and therefore they can't be tied directly to Galois cohomology or to anything algebraic. So the Kudla program sort of postulates that there are all these fascinating generating series which involve heights in the Arakelov sense of special cycles on Shimura varieties and so on. But the way that these formulas are proved are very much in a kind of Gross and Zagier spirit, where one sort of just finds the cycles. And so one has already a good algebraic and arithmetic understanding of these invariants, and then one just computes them and verifies that they're equal to the coefficient. So, but in a lot of the settings that we explore here are settings where there is no visible connection to algebraic cycles. So there might be something else, and that's what we're trying to understand. But yeah, I mean, so that I should say that that's certainly another big question, maybe even less accessible than what I've mentioned at the end, to try to understand the Archimedean constructions.
So sorry, maybe on this question, I just want to mention that I think Jan and maybe Mikolaj Fratzik, which is another postdoc at the IIS, have thought about defining at least this kind of rigid meromorphic cocycle in the Archimedean setting and ATR points. So I don't know, Marc, if you want to ask them, they might have some answers about that.
Okay. Yeah.
Yes, that's right, and they also have some interesting ideas about getting actual heights. I mean, the kind of invariants they're constructing seem to be related to values of certain Archimedean Green's function, or conjecturally, of course, what should be values of Archimedean Green's functions at these kind of objects. So they'd be getting maybe invariants that are closer to Gross Zagier, because in Gross Zagier one gets narrow Tate heights, right? That involve. So yeah, I mean, in a sense, yeah, that's certainly very interesting. I don't know. I mean, maybe McGill, you know more than I do about how far along they are in this direction.
Oh no. I mean, last time I talked to them about this was December, so I don't know like if they got farther than this.
Yeah, I mean, I know that Akshay has also been working with them, and he has the idea that one should get maybe conjectural Gross Zagier type formulas involving heights, Archimedean heights in this setting.
So it should be a little bit more accessible than the ATR construction, but still very, very deep.
I don't know how. No, I think that they really are trying to, right? I mean, they're trying to construct meromorphic cocycles in this purely in this ATR setting, and working through the analysis that would be needed to do that.
Nice.
I mean, I think that, if I'm not mistaken, what they're trying to do is to define really a Green's function on something like H cross H mod the Hilbert modular group, which they can then evaluate some way on.
Nice.
But this Green's function would be a cocycle, right, on the Hilbert modular group with values in some functions. Maybe on functions on H cross H, but maybe with some kind of logarithmic singularities along some divisors.
Nice.
There's a question. If not, so let's thank Henri again.
Well, okay, let me thank you also, because I feel like now I finally had the chance to pay back after 3 months. 3 months after I was very well received in Barcelona, so it was quite a pleasure to see you all, even virtually like this, and give this lecture.
Okay, so thank you.
Yeah, so I hope you're all staying well. I mean, and
So.
Okay. Oh yes, I'm going to now. Let me just stop.